All right, welcome. We have a packed day today, so let's get started. Wednesday, Thursday, in our case Thursday, is our last lecture, and we will try to have a review. I'm not sure I'll have the material available by Thursday's lecture. I probably will need the weekend to do it because there is one more lecture that Monday has, and I want you guys to be able to take advantage of that as well. But the final is going to be just like the midterm in that it's an hour and a half long. I will probably drop the low question again. That seemed to work miracles. I was very happy that with the strategy we took this time, the low grade was almost double of what it was the prior year. So I plan to stick with that. I love that. And so the grades are out on Blackboard for the midterm finally. It's like a bucket list item almost. It's taken so long. So that's all coming up. I can have extra tutorials or short video clips if people have particular issues they want covered. Like, can you walk me through this again? Something like that. Sometimes little 10-minute videos work really well in that. And so just let me know if that's something you want. Now, we had a request to go over the last problem on the homework. So let's go down here and take a look at what's going on. So fragments are tricky, and so I've walked you through kind of what this is in a little bit of detail, but let me try drawing to kind of help you out on this one a little bit. When an IP datagram is originally sent, it has a header and a payload. And normally a payload contains, let's say, just for grins, a TCP packet. So TCP is going to have its header in here, and then it's going to have the message from the program, from the application layer. So if you find before you drop this out onto a network that the physical network itself, the frames, let's see, Ethernet frames, have a certain fixed maximum size, which they all do, 100% of them do. Every network has a maximum packet size that it can handle for among other reasons to keep people from hogging the network, but also because of reliability issues. Typically, smaller packets suggest higher error rate or the need to very carefully control behavior, like emulating a perfect circuit switch network for voice and video with no possibility of drop packets, for example. Ethernet, typically, most Ethernet networks have a maximum frame payload size of 1,500 bytes. And that runs from here to here. So whatever you put inside this has got to fit within, if it's an MTU of 1,500, and that's the name of the variable that defines this, it's got to fit in within that. So what are they talking about? They're talking about this whole thing can't be more than 1,500 bytes. So what happens when this is too big? Let's say it's 8,000 bytes long, all the way from here to here. Well, clearly you're not going to be able to fit all that in there. So what you start doing is dividing the thing up. But each one of these things is going to be put into an Ethernet frame, and when it gets to the next router, the router is going to have to be able to look inside of it and figure out what to do. Well, what does that mean for a router? Well, routers run at layer 3. So for a router to be able to look at a frame and figure out what to do, first of all, your Ethernet card is going to throw away the Ethernet part, and it's going to hand whatever is inside to whomever the Ethernet frame's protocol type says to give it to. So if it's IP, which it is 99.9% of the time, then the protocol field inside the Ethernet header will say to the Ethernet card on the router, hand this up to IP. You can hand it up to other things. There are other technologies, but we focused on IP in this course. So we'll hand it to IP. So what does IP expect? IP has to have, among other things, a header, right? So everything the packet looks that the IP software looks at in a router expects it to be a regular IP datagram with an IP source and destination address and a payload with a link and the whole bit. So you can't, as a result, just come through here and chop this thing up like this because your header is only going to end up in the first one. And there has to be a header in every IP datagram. So, the router wants to be able to route these things separately. So what you have to do is instead preserve this and chop up the rest. Right? So you'll throw out any options that you can, and the smallest IP header is the best choice. So you try to go for that. And the smallest IP header is 20 bytes. So in all of my exercises for fragmentation and in the book, they always use the smallest possible IP header. IP headers can be bigger, but it makes this exercise overly complicated for learning what fragments are. So we know for every IP datagram, we're going to have to keep the 20-byte header so that all of the fragments arrive at the same destination IP address, so they can be reassembled for the original intended recipient, because this entire 8,000 bytes here is intended for, let's say, a website. That's what we're trying to send this thing to. So, of course, every one of the fragments, once we break it up, we also want them to also go to that website so they can be put back together again. So you will need the same IP header on all of them. There may be slight variations in them, but that's generally what we're looking at. And so the variations are going to be responsible for, if I were to number these things, 1, 2, 3, 4, 5, 6, to help the receiving site know a couple of things. First of all, that they're fragments. That would be good to know, so they don't interpret it as, you know, the one that includes the header, let's say, in just this piece, so it doesn't get interpreted as the whole thing. We want it to know that they're fragments. We want to know how to put them back together. Packets arrive out of order all the time. They get duplicated and dropped all the time. So if 4 shows up before 2, we don't want the receiving end putting them back together 1, 4, 2, 3, 5. They need to put them back together 1, 2, 3, 4, 5. So there needs to be information in the header to let me know that, you know, where this fragment goes, and when I'm done, it needs to let me know that I'm finished. So how are we going to do that? So what we're going to do in each one of these headers down here is we're going to put the, whoops, didn't change my colors. Hold on here. There we go. We're going to put the IP header again in every one of them. That's going to take 20 bytes up, and it's going to leave us with 1,480 if we need it. And we'll fill these 1,480 remaining spaces up as much as we can. We'll pack them completely full, and until we don't need, you know, all of them, which would be only the possibility to be the very last fragment. Maybe the last fragment doesn't need all 1,480. I mean, it would be a little odd if your payload was a multiple of 1,480, but it's possible. So I start off with 8,000 bytes I got to send, and my payload, I will always tell you guys how much payload there is. So what I'm going to tell you in these problems is this is how much data you have to send. So you're going to start from this point. I will give you this number. I will probably not ever make you start with this. All right, so I will just tell you it's 8,000, but I'll really just give you this number. So you have, let's say, 7980 to send in data. All right, so we begin. First fragment, what are we going to have? We'll have 20 bytes of header and 1,480 bytes of payload out of the 7980. All right, so if I subtract that off, then it leaves me with 6,500 bytes to go. Okay, that worked out great. It's a mistake. Then that's going to be fragment one's going to get me down to there. And then the second fragment's going to take more off of that, right? And it's going to leave me with 5,020. And the next one's going to leave me with 9,543, I think, something like that. It's going to leave me with 3,940 and so forth. Sorry? Thank you. I'm trying to think ahead to whether these are multiples of 8, which is they're probably not going to be. All right, so I'm going to subtract this down until I just run out. And so this will be one fragment will get me down to here. The second fragment will get me down to here. The third fragment, and so on. So what's the labels? What's the data that you see in the table on the left? What are those fragments going to look like? And why do I not see video? It's kind of weird. Why do I not see it? So there's my video. Why was my video not in there? Makes me very suspicious. You guys can still hear me, right? And my audio's there. Why would my video not start? It's never done that before. Okay, so hopefully I don't see any pleading messages like, we can't hear you, so I guess I'm still there. Okay, so the data length is going to be however much you put in this one, like 1,480, for example. The more fragments flag is a flag that's in the Wireshark trace. You'll see it when you look at the PCAP file that I gave you guys. And the flag is set to 1 whenever there are more fragments. So it's going to be set to 1 here, and 1 here, and 1 here. And when you finally get down to the very last one, you'll set it to 0. That's how the receiver will know there's no more fragments. But that's not everything I promised that we needed to tell it. We need to tell it there's no more fragments, but we also need to tell it where this thing fits in. So again, if the packet that contains this piece of your original datagram, which is now what you and I both will recognize as a fragment, but which the world's internet thinks of just as some random IP datagram, what if this one shows up early before one of the others? How is the receiver supposed to know that it's the 4th one and not the 2nd one, even though it arrived, second? So the way you do that is with the offset field. And so the offset is going to tell you from the original datagram, starting at byte 0, running all the way up to, in my case, 7979, which is the 7,980th byte. Since I started at 0, I ended there. Where does this particular fragment that I'm receiving fall in that range? And the offset field will tell you. But we don't have enough bits to specify down to exact byte numbers. We only have 13 bits in the offset field. So like we've seen sometimes before, we have to do things in multiples. So header length, if you look at that in a Wireshark trace, the header length is also an example of a field in IP where we don't have enough bits to specify exactly the length of the header. So we force you to make the header multiples of 4 bytes. So the number that's in the header length is actually to be multiplied by 4. So if you find 5 in the header length, it means your header is 20 bytes long. So let me see if I can find this. Large ping trace. All right, here it is here. So here's a, what I want to look for here are some IP datagrams and some fragments. Okay, so here's an IP datagram. If I look at the flags, it's a fragment. If I look at the header length is the binary number 5. 101 is 5. But it's a field where I didn't have enough bits to specify 20, so I make the header, I force it into a multiple of 4, and then write down what that number is here. So 5 here represents 5 quartets. Same thing when you get to offset. We don't have enough bits. You see there's 3 missing here. I needed those for the flags. So I only have 13 bits instead of 16, so I'm going to force you into multiples of however many bytes I lose by taking away 3 bits from you. Well, 2 to the 3rd is 8, so I'm going to force the fragment size into a multiple of 8 bytes. So if you are trying to send a fragment and it's not a multiple of 8 bytes, you have to change it to make sure that it is. So 1480 is, you can fill that up. Fortunately, as you can see here, I do not know how to type. 1480, thank God, is a perfect multiple of 8. So each 1480 byte payload is 185 octets in length. So if you want to try to tell me that this first fragment is 1480 bytes long, you will do so by putting the number 185 here in binary. So what is 185 in binary? I'm glad you asked. You won't need it for the problem, but just to kind of show you, it is 10111000. So if I come down to the next fragment, this one is a fragment that starts at offset 0. So this is the first fragment, begins at the beginning, and I have my total length is 1500. The header is 20. So this is one of those packets. This one has 1480 bytes of payload. So it's going to start at this 0 point up here, and it's going to get me up to byte number 1479. So the next fragment is going to start with byte number 1480, but I can only put octets in there, so I divide it by 8, and I'm going to get 185. And let's go look. This one should be one of those. It's 1480 bytes of payload, so let's move down and look at the very next fragment. And in this PCAP, they're all in order, so it makes it a little easier. And here it is, 10111001. This next one starts at offset number 185, which means it starts at 185 times 8 equals 1480. So when this one arrives, it's 1500 bytes long. It'll have a 20 byte header, and it'll have 1480 bytes of payload. And you know where to put it, because when you multiply this back by 8 again, it'll give you 1480, and you'll know 1480 is here. So if I'm building this at the receiver, all I know so far is I have some unknown length datagram that's arriving in fragments. And I know it's a fragment because the more fragment bit is set, and the first one started at 0, and the next one started at offset 185, better known as byte 1480, and that's all I know. I have no idea how long this is going to go on. I have no idea how many fragments there are. I don't know what the original size of the datagram was. I will know that only when I receive a fragment where the more fragment bit is not set. It's set to 0. And whatever that one is, that offset number here, if the MF bit is also set to 0, then this is the last one. So what I'm hoping is that I get this one, maybe the next one I get is the very last one. But if this one was 0 and this is 185 and this is something like 800, then I know I'm missing some in here. So I have to wait for them. Maybe this one arrives next, and then this one arrives, and then when this one arrives, I can see that I have a continuum, that I'm not missing anything, I have no gaps. I finally have reassembled what IP handed down to Ethernet to begin with, or what TCP handed to IP to begin with. And so I can reassemble throughout all those extra headers, and finally throughout my own final header here. This is what the user TCP stack at the other end was trying to give me. This was the original orange payload in here. It had a TCP header, and it had all this stuff. So now I've reassembled that. I have all this payload. It should look exactly like this one did, and I hand it up to the application. Mission accomplished. I hand it up to TCP. Okay, so that's what I'm after. So if I go to these are 3 fragments a piece. I look at the last one. It also has an offset. It's 370. This time the more fragments bit is not set, so I know it's the last one. So if everything went well and these things showed up in order, then I've got them like I want. So let's go do one live. Let's build one and see what happens. All right, so I'm going to open up Wireshark again, and I'm going to open my terminal window. And there's one other thing I need to show you. So think about what happens at a server. It's receiving millions of packets a minute. Some of them are fragmented, some of them aren't. So these things are showing up. Some of them are whole packages, some of them are pieces of packages, meaning fragments. How is it supposed to know how to put these things back together? If it's an entire datagram and it shows up with an offset of 0 and it says there are no more fragments, well then you know that's the one and only one. Starts at 0, nothing else follows me. It's the whole thing. Easy. Got the whole thing done, done with it. Send it up to TCP. What happens if I receive a fragment? Something that either doesn't start at 0 or has the more fragments bit set. That's something where I need to set it aside and reassemble it. Wait for the other pieces. So when another one shows up, and it's also a fragment, and it also has an offset, how do I know it has anything whatsoever to do with this other one? I mean, there could be 1,000 computers on the internet sending me things that get fragmented at any given time. It's very likely, in fact, especially if the fragmentation happens because the MTU close to me is too small, then everyone's datagrams are going to be getting fragmented. So just because I get a puzzle piece in the mail doesn't mean it goes to this jigsaw puzzle I'm working on. Maybe it's a part of another jigsaw puzzle I'm working on. Maybe I have 100 jigsaw puzzles I'm working on. So when I receive a piece, it's not enough to know it goes in the 4th row and the 3rd thing over. I got to know, like, which jigsaw puzzle is it I'm working on here? Slow down. So I want to turn the piece over and look on the back, and it's going to tell me this is the Eiffel Tower jigsaw puzzle you're working on, or this is the Notre Dame crossword jigsaw puzzle that you're working on, or whatever it might be. So what is that field? How do I tell what that field is? That, it turns out, is the identification field. It's the same for every fragment. That's how you tell what original datagram it belonged to, and I'll show it to you. So what I'm going to do is I'm going to ping someone, and I'm going to forget the command. Really? Okay, let's Let's see if I can find the link here. I think it's S. Yeah, it is. Okay. Ping S 8,000 bytes to www.rice.edu and see if it comes back. It did not. So let's try it for U of H. First, we got to find something that'll answer it. Wow. Interesting. Never seen that error ever in my life. How interesting. That I got to trace just to see what's going on. Okay, so let's try that. Now what I'm going to do is just filter for IC&P errors. Okay, we'll stop, and I'll stop. All right, so I'm going to pick one of these. Oh, I know one reason. One thing I got to do is I got to turn off monitor mode. Yeah, I got to do it again. Yeah, I don't know if it's going to work the way I want because these are weird errors that we're seeing over on the right. The nice thing about the internet, working on this, is just like you see a new error. Like how many years I've been in it? 40 years. I see a new error. Whatever. It doesn't really surprise me. It just interests me. Okay, so I'm going to pick one of these. Here's a reply, and I'm going to turn off my filter and see if I get lucky here. So here's some fragments. They're each 1,480 bytes in length. I intentionally sent a ping that was so big that I was hoping it would have to be fragmented. And as I come through here, I'm going to look at my IP datagram. I've got to start with the first fragment. And you'll see an ID number, 76B5. Then I go to the next one, 76B5. A couple more down, 76B5. If I go to some more down here, see if I can find some more, reinstate my filter again. I want to find some more of these guys. Okay, move down some more here. Here's a reply. It's so much further down because of all the WebEx packets I have to kind of search for it. 9BE7, not the same. So if this one shows up, I know it does not belong to the B765, whatever the other one was, right? And here you can see a total link. You can see a header link. You can see a, if this one is a fragment, it's got the 1-bit set and an offset of 555. So what byte number is this? 555 times 8. This is the packet that starts at byte 4,440. All right, makes sense? Hope that helps. All right. Hopefully we'll kind of get you through it. Data still to send is this, whatever the remainder is after subtracting the 1480 off. Okay, so that should be able to get you through that. Okay. If you did not listen to the recording from last Monday's lecture, since we didn't have Tuesday lecture, which for the record is the only class we've missed this semester and only the second one in 20 years out of all classes I've ever taught. But I was on a plane. I tried doing one on a plane before, just for grins, not a class, but another WebEx, and it didn't really work all that well, but it didn't really work all that bad either, which was sort of fascinating to me. So what we covered in here was a different link layer protocol, and we covered MPLS. And there's two things I kind of mentioned that I'll highlight now that I want to make sure you take away from it. One is that we mess with the layer 2 and layer 3 headers, but in this particular case, layer 2 headers, all the time. We have new versions of them that insert more data, but you will usually never see it because these headers are used between networking equipment, pieces of gear. They're not typically used between your device and the networking equipment. So think about between routers or between routers and telephone company equipment. So we talked about VLANs 2 lectures ago, where you can have switches inside of a local network emulate a LAN, even though people are physically separated on different physical LANs. They can still join them back together with magic and make them act like they're and believe they're all on a LAN. This is the same idea, but for the telecommunications industry. So if you connect all of your offices around the world to Sprint's MPLS cloud, it's a layer 2 network. They don't care what IP addresses you use. You can use the same ones that another customer is using. They don't look at your IP address. There's no way for it to be a conflict or cause them a problem if they don't even look at the thing. They couldn't care less. What MPLS does is set up point-to-point layer 2 connections So kind of a shared cloud just like VLANs do. It's a very similar idea to that. So take a peek at that, and that lecture is one that you definitely want to look at. And then there's some fun stuff here at the end on data centers and power utilization efficiency, and we take a look at a website that kind of helps people gauge how well are you doing at running your data center as far as keeping track of power. And then very, very critical, and I'm not going to go over this again for you today, you need to make absolutely sure you spend some good quality time with the day in the life scenario in the book. And I walk through it in the video, and I give you some hints on what you're going to see on the final that regard this. I don't know if I'll give you a homework problem on this one. I will certainly give you stuff on the study guide to kind of look through, but this sort of pulls it all together. So you're going to need to know, you're going to need to be able to follow along and know that when you show up on campus and you turn on your laptop, the first thing you need is an IP address. So you're going to send out a DHCP broadcast. And when you do that, your IP address shows up as all zeros because you have no IP address. How could it be anything else? And it broadcasts out to everyone because you don't know who anybody is because nobody's told you anything yet. And then on from there. So I'll give you a series of these things and ask you to kind of put them in order. But take a peek at the video. It'll walk you through a little bit more of what you need on that. Okay, so today what we want to dive into is wireless. And I'm going to skip over some of the stuff that we don't really need because we have one less lecture. So I'm going to skip past some of the stuff that's fun and get us to the stuff that we need. You guys know much of this stuff anyway. There are lots of wireless protocols. Some of them are for networks that flood a certain geographic area with coverage, like a cellular network or a Wi-Fi network, or a television network, for example. And some of them are directed. They're point-to-point wireless networks where you try very hard to contain the signal into as narrow a beam as possible. And so this would be what the military would use to beam down images from a satellite. They try to beam it down in a narrow enough place that it only hits a satellite farm in Arizona as opposed to Russia, for example. And I have a picture of what one of those looks like. And usually it's deadly bad idea to try and go fishing during a lecture, except I struck like super big pay dirt yesterday, and the very first one I looked at, I found one. I don't think this is my picture. I think this is a stock photo. But these look different than the vertical cellular radios that you normally see. These look like parabolas, more like parabolas, and they are. They're intended to send a signal in a very narrow beam. So you'll use this to relay signals from one tower to the next across the country. And this is the way our long-distance networks used to be built before we dug cables everywhere across the country. So you'll still see these towers. They're still painted just like this. There's one on I-45 as you leave Houston, up past Spring, I want to say. And it's got older types of dishes. Most of these have been abandoned. So you'll see on tall telephone company buildings and things. Let me see if I can find some in here. Let me see if I can find another one. Yeah, so here's one in Monterrey, Mexico. And you can see it has very little left on it. So the ones that are left here are pointing to ones on tops of mountains or in other communities. Maybe Telmex doesn't own the land in between. This one has to go across a river, so does this one. This one goes over a mountain, Cerro de la Silla, and goes around it, etc. So they'll still use it sometimes when it's still possible but expensive to run cables. But that's a different type of network. The Wi-Fi, other stuff you guys know well. You've seen that before. So just know there's a variety of things out there. So what we are going to spend some time on today is taking a look at how wireless is fundamentally different than cabled networks when it comes to collisions and error correction, error detection. And so one of the most important fundamental things I want you guys to realize is there is decreased signal strength, that the signal deteriorates at orders of magnitude more quickly on a wireless network than it does on a wired network when you measure the amount of energy you receive. So with a Ethernet cabled network, it's an example of what we call guided media. We guide the signal down a very specific path, the path of the wire, or the path of the fiber, for example. Or if it's two cans in a string, the path of the string. which I could never, hardly ever get to work as a kid, by the way. Worked better if you use monofilament than if you use platinums. We didn't have that. So, hey, we didn't have ones and zeros when I was there. We just had zeros. Ones came along later. We had to wait for that. And we also didn't have electricity. We were so poor we had to watch television by candlelight. All right. So key signal strength, that's guided media. So think about it. I've tried for years to come up with a good analogy. This one's a little gross, but it's a lot less gross than some of the other ones I've had. So suppose I want to give a piece of gum to you. Okay, like we're dating in high school, and I'm going to share a piece of gum. So one thing I can do is roll the piece of gum down the table, and some molecules of the sugar in gum will fall off, but you will get substantially the entire piece of gum at the far end of the table. So that's one way to do it. That's guided media. Preserves most of the signal strength. So what that means for Ethernet is the standard is set, and the voltages are defined in the standard, and the lengths of the cable are defined in the standard to guarantee that no matter how far apart you are from the other person, as long as you are within the standard, there's zero possibility, none whatsoever, that you will not be able to detect any signal they put on the wire. Yes, it will get weaker as it goes along, but it's such a short distance compared to what it would take to really deteriorate the signal to a point where you couldn't tell that it will never happen. So this is why you can hear collisions. If you just listen on an Ethernet network, you will listen long enough that you will detect the collision. It's not going to be so faint that you can't hear it anymore. Okay, now let's switch to wireless. And now what I need to do is get the gum to you, but I'm sending a radio signal in all directions at once in a sphere. So I'm going to chew the gum and blow a bubble instead. And I'm going to blow a bubble, and I'm going to keep the bubble centered on where I was standing when I started to chew the gum. So as I blow the bubble bigger, it's getting close to you, but I'm also backing up to keep the center of the bubble there. So it's only the radius of it that's getting close to you, not the diameter of it. So if it stretches 2 meters that way, then I'm 2 meters back on the other side as well. So when it finally gets big enough to reach you at the other end of the table, it's this magic gum, it doesn't pop or anything, and you have an antenna that's 1 centimeter in size, let's say, how much of that original bubble of gum in terms of mass are you going to actually be able to pick up? Almost nothing. You can picture that in your mind. Like you can imagine all of those little 1 centimeter squares around that bubble. So that's all that wireless antennas, receiving antennas have to work with. It's also all yours has to work with. It works both ways. That tiny little antenna in your radio is small enough to receive a signal from the cell tower. And the signal from the cell tower is going in all directions at once. So they do a couple of things to cheat to help them that you don't get to do. One of the things they do to help cheat is they make the antennas a very specific shape, and they aim them in a certain direction. So they can tell which radio your signal is arriving at. So they know on which side of the tower you're standing. And so when they send a signal back, they send it with the radio that points back at you because they know where you are. So they don't have to send it all the way around the tower. They actually do send it just in your direction. So that helps a lot. But you don't. You don't have anything. You don't have a little thing that's like on top of your head following the cell tower as you move around, you know, like one of those geostational deals. No, you send it in all directions. And so what's really very surprising about this, it sort of catapults it into the area of magic. And it was the day I decided this is why I can never be an electrical engineer that designs antenna arrays. Let's say you're, what's the example that I come up with yesterday? It was really great. I'm going to forget. Downtown, let's say downtown. I thought of a site that made everybody here would know. I'm sitting downtown, and at the end of one of these very long streets, I see a cell tower. It's, in fact, one of these white antennas on the side of a building, so it's not even a tower downtown. And I have my phone here, and I start sending something, and of course the signal goes out in concentric circles all the way around, and I can draw this as a set of vectors if I want. So one of the vectors would be the signal that goes directly to the cell tower at the end. And it's a bubble of gum, so it's a tiny little piece of it, right? And so there's a sine wave that's arriving there. It's very weak, but if it's within the standard, I should still be close enough. I could be, you know, a kilometer away from this thing. Imagine that bubble. And it's still strong. With just a little battery, mind you, just a little tiny battery in my phone, it's still enough to get a signal. So these are larger antennas, and they have ways of getting things back. But here's the deal. I send my signal out in all different directions. So a copy of it bounces off this glass on this building here and also arrives at the cell tower, whatever the extra amount of time is required traveling at the speed of light to go this extra distance. So almost at the same time. And it's slightly out of phase with your signal because it took longer to get there. So if your signal looked like this, then that one's going to look just slightly out of phase. And then there's going to be 1,000 more of them that show up as well, that bounce off of every other surface and get there. That's some that bounce off of the wet ground and maybe a plane flying overhead. And so a weak copy of it gets there a little later. So all of these things are arriving at once, and the tower has to figure out how to put that back together somehow. Not only that, but this is an antenna. It receives all RF radiation in those frequencies, and the frequencies it used for cell phones and Wi-Fi overlap with some other things. Cell phones are less prone to this, but Wi-Fi is a non-licensed spectrum. So, if AT&T finds somebody using their spectrum downtown, they can make them stop. Legally can force them to stop. Fine them, sue them, everything else. They can get in big trouble. When Wi-Fi network, no one's going to stop someone from bringing another hotspot. If I turn my Wi-Fi hotspot on my phone, which I'm going to do right now, presto, I'm now interfering with the signal between my own laptop and the Wi-Fi router in this classroom. And so nothing will stop it. So there's thousands of other signals that are arriving potentially at one of these receivers in a classroom, maybe dozens, as well as the stuff coming from the classrooms around us that are connected to other Wi-Fi networks. So it's very difficult to sort this stuff out. So what this book does that I like very, very much is they spend a minute talking to you about how the encoding happens. All right, so a couple of other things about the differences here. The signal attenuates very rapidly because you're trying to blow a bubble instead of roll the gum across the table. So in this case, B is the Wi-Fi device in the middle. A and C both want to send something to B. Now, when we talked about the Aloha network, that wireless network had a problem where A and C couldn't see each other because they had a volcano between them. So even if they tried not to interfere with each other, they couldn't do it if they tried because they couldn't hear each other. It's the same idea with smaller wireless networks like Wi-Fi, but here the problem is I'm just too far away. See, in A and C here, it looks like they're physically close to each other, but impeded from hearing each other. Here, A and C are not physically close to each other. They're so far away from B that they're barely able to get a signal to B. And they're certainly not able to get a signal to each other. It's too weak at that point. So they can both try and listen to avoid causing a collision, and they can both wait until they think the network is free, and both try to send something to B, and still collide simply because they couldn't hear the other person talking. In fact, A could be talking in the middle of talking, and C won't even know. So collisions are not detectable, always not detectable. I mean, sometimes they are, and they're not always detectable, and so you cannot count on knowing whether there's a collision or not. Therefore, we're not even going to try. We're just going to throw it out. We're not even going to try to detect a collision. It's pointless to do so. If you hear garbled data, you wouldn't know whether it's a collision or somebody started up their microwave oven. They use the same frequencies. So how would you know? Or you might not know that it's Kevin turned on his phone. That's a collision, but it's not anything any of my Wi-Fi users did. That's some other Wi-Fi network that popped in. So we're not even going to bother trying to do it. All right, so let's take these in order. First, let's go back and figure out how do I pick out your signal from all the others, and then we're going to look at how do I figure out what to do during a collision. So with CDMA, which is the cellular network technology name, I write these things and then they get reformatted. I never really know how that happens. What we have is a chipping sequence, which is not something you do at the golf course or just at the golf course. What I'm going to do is something similar to what I talked about when we discussed how to encode digital data. And if you guys remember, when my sine wave started getting fast enough, what did I do? Hide the background? Yeah, I did. It's my first day using a computer, so you'll have to forgive me here a little bit. Oh my God, how many times am I going to click on that? Okay. And I have to get the right tool up too here. One of the things I talked about before is you can use multiple signals. You could call this a 1. And then you can call this a 0 if you want. This is different than the one I showed you last time. There's lots of encoding schemes that you can use. So even if it gets corrupted and it shows up as this, if I asked you, you would say, yeah, that's still high and primarily low and high and low. This is the 1. And this one's high for a couple of cycles and more low than not for a couple of cycles, and it's a 0. And the advantage of this is you're using multiple passes of the sine wave to encode a single bit. When you could have, you could have made every one of these little peaks and valleys like mean analog voice data or something. But we gave up doing that, and we switched to 1s and 0s and used lots more frequencies because it adds lots of redundancy to the signal. Therefore, it adds lots of reliability to the signal. And the beauty of doing digitization is when this is received at a point where I now need to repeat it, I can figure out it was a 1 and 0, forget the blue line, regenerate something that looks like the red line. So you can generate a new perfectly pure signal. That wasn't possible until we started digitizing signals. So what you see here is a similar idea. I'm going to use lots of sine waves to encode a single piece of user data because it adds redundancy and reliability to it. So in this case, I'm given the user a chipping sequence, and it's a series of positive or negative numbers. And in this case, it's 3 positives, 1 negative, 1 positive, 3 negatives. That's their sequence. It's unique to them. It's given to them when they connect to the cellular network. And it may be given to somebody else later, I suppose. And the first bit of data that you actually have to send is a low value. And it's not 0s and 1s. We're going to call them negative 1s and positive 1s. But it's still binary. It's just not 0 and 1. It's still 2 possible values. So I don't know. Maybe this negative 1 and plus 1 is part of the beginning of an Ethernet frame or something like that. Who knows? It's just 2 bits of data. So what I'm going to do to transmit this is take this and encode it into this chipping sequence. So I'm going to go through here and multiply my data by the value that's shown. So my data is negative 1. So it's going to turn this into negative because I'm going to multiply them. It'll turn this to negative, negative. 2 negatives make a positive, so this one will be a positive. This will be a negative again, and positive, positive, positive. My next bit of data is a positive 1, so we'll leave it alone. So what you end up with is something that looks like that. This one is a mirror image of my chipping sequence, and this one is exactly my chipping sequence. With me so far? And when I receive it at the other end, what I do is basically multiply it back by the chipping sequence that I am looking for. So if this is a network that right now only has 1 user on it, then I've received this funny looking sine wave signal with negative 1s and positive 1s, and I want to figure out if it's from you. So I take this and I multiply it by your code, your encoding code. And what I'll figure out when I do that is this turns out to be, if I add this thing up, I'll figure out how to extract back the data again. So let's see what I received here. This one will give me all negative 1s. You see that? And this one will give me all positive 1s. It won't give me a mixture. So the only way this could be a single number all the way across when I multiply the received data with the code that was assigned to you is if it was really encoded with your code. Somebody else has a different chipping sequence. It won't give all 1s. It'll give maybe mostly 1s and then a negative 1. I'm like, darn, it's so close. Okay, this isn't this guy's data. This is somebody else's data. Right, so that's something you can use. And the cell tower knows whether to expect you or not. You do have to associate with it. To get a little more interesting, if you do 2 users at once, each of whom has a slightly different code, the first person has the same one. It's the same user. The second person has a different code. This one has data to send of -1 and 1, and this one has 1 and 1 to send. So you encode each of these things together. They each come out with their little sequence, but then you add them together because it's radio waves. They combine. And so what you end up with here is this person was trying to send a -1. So his code says, keep it. Don't reverse it. So -1 is output for this first time sequence. This person is trying to send a 1. This first code says keep it, don't try to reverse it. So he produces a 1. This guy -1, this guy 1, they combine for 0. So there's flat carrier signal here. The second opportunity I have to encode is the second time slot. -1, this says leave it alone. This is 1 that says reverse it. Now I have a -1 and another -1. That gives me -2, a stronger signal in the negative direction. So I end up with this being transmitted over the airwaves. I receive it back at the receiving end, and let's say I want to pick the first user's data out of it. So what I do is I crank through this thing and multiply it by my code, and what I'm going to get is, you know, 1s. This will make it a -1. I add these things actually here. So 0 plus 1 is 1, -2 plus 1 is -1, 0 plus 1 is 1. So far I've matched. I've matched this code that I was trying to use. And so I can extract my data back out. So that's kind of the idea. So that's a terrible 10-minute, you know, rush version of an idea. Hopefully it's intriguing to you and at least gives you a little confidence that indeed there is a way to combine lots of users' signals together on like a CDMA network. Code division, multiple access, CDMA. So this is how you do it. You give everybody a different code and they encode. So it's very clever. Works great. And it allows you to send lots of people saying as long as you have enough codes. All right, that's the first thing I wanted to show you. I told you there were 2 things I kind of wanted to get through. The second one is how Wi-Fi handles collisions and what's going on. And so this one's actually going to be more fun. All of these networks, including 802.11, don't worry about collision detection. They worry about collision avoidance. There's no way to detect a collision. Right? We already talked about that. Okay. So a bunch of standards. We don't need to know this stuff. We know what Wi-Fi is. We've used it before. You can listen for SSIDs to come rolling in, or you can specifically probe for one. So sometimes, if you've noticed, you can join another Wi-Fi network besides the one that's from the list that's shown. Maybe you are trying to connect with an SSID that is hidden, and it doesn't advertise what's going on. So if I show you back in Wireshark again, and it looks like we can see a few here. In fact, if I do my own, I should be able to see this again. Whenever you're ready. Okay, it's my laptop. I'm sorry. And so I'm going to go to options. I'm going to turn monitor mode on because that'll give me lower level data. And what I'm going to do is just, did I select the wrong one? Apparently I did. Apparently I selected Ethernet. Yeah, what a moron. Okay, let's try this again here. And I'm going to turn mine on again. And so hopefully it will cause some beacon frames. And I'll see if it shows up over here. Come on. Come on. Let's do it again. Show up here. Again, turn it on. I'm going to try to get some beacon frames out. All right, so that should be enough. So what I want to do is look for some beacon frames up here. Here we go, right here. So here's where the UH Secure network is advertising its existence. There's a broadcast one that's being advertised, wireless. If I want to, I don't know what the filter is for beacon frames, but we can try searching for it. There's a million of them, so it's impossible for me to remember a bunch of them, but I'll try. Let's see if we can find one. And I want to see if I can find one for my phone. And it doesn't work half the time, so hopefully I will, but there's no. Here we go. And that's not the one I want. I don't want that beacon either. 802.11 fixed beacon. I have no idea if that's what I want. Let's see if it'll give me. No, it did. It's a miracle. Okay, so if I scroll through here, do I ever see one from me? That doesn't look like it. But there are some different ones in here that look like it. So you can sit back and wait for the beacons to show up. That's one thing you can do. Or if it's a hidden network, like mine's trying to be, you can try and do it that way instead. Okay, so how do we avoid collisions? Remember, it's CSMA-CA, Carrier Sense Multiple Access. That means you will listen to see if the network is available because there's multiple people using it. With Ethernet, do you guys remember what the acronym was? It was CSMA-CD. This one is CSMA-CA for collision avoidance. So what you're going to do is ask permission to send something. You will raise your hand briefly and ask the teacher if they will call on you. And if the teacher agrees, they will call your name. So let's say I'm sitting in the front row and I raise my hand and the teacher, I think, is looking right at me, but she calls the name of somebody behind me. Oh, they must have had their name up, their hand up too. Didn't mean to collide with you, sorry about that. But obviously the teacher called on you, so I can put my hand down for a while. I'm not going to get to speak up and ask my question. So that's the way you ask permission in Wi-Fi, is you will send a very small packet asking for permission to transmit. And provided it doesn't collide with somebody else, like you don't slap the person next to you with your hand against theirs when they raise their hand at the same time, as long as you don't cause a debacle like that, which is very rare for that to happen, then if you get called on, then you can talk for a while, a lot longer than it took you to put your hand up for a second. So that's the idea. We make the requests to send information really, really short. That's the strategy. Make them small. The smaller they are, the less time they're on the network, the less chance they have of colliding with someone else. So we avoid collisions by sending very, very tiny, short requests to send packets. You may send thousands and thousands of bytes for your payload, but for your request to send, you're gonna only have a few bytes, 30, 40 bytes. All right, let me see if I can find this in here. I dream of a day when I have like a fast computer. I feel like I'm at a third world computer or something. I kind of do. Okay, let's see if I can find it in here. 802.11 are the numbers at the end. Here we go. That's really not what I want. How about try this. Request to, come on, you can do it. Just narrowing it down letter by letter. And I'm going to probably narrow it down to where there's like, yeah, of course. Absolutely nothing at all. Oh. And then I have to wait to like backspace, correct the T to a D. Okay, good. Back it up a little bit. 802.11. Yeah, I'm not going to be able to find. So it's here. So I just won't be able to filter it. That's all. So I'll just get rid of this one, and you'll see them. There's tons of them in here. So you have a request to send that you blast out, and I don't see too many of them in here, which is really quite interesting. If I sort by this, I should. Beacon frames. Then I have acknowledgement fields. This is data, block apps, more beacons, clear to sends. Where the hell are the requests to send? I did something to Wireshark the way I filter this to keep them from showing up. They're in here, but there actually should be many, many thousands and thousands of them. They were here yesterday, but I screwed it up with my filters somehow. So, yeah, like that's a big surprise to anybody. Okay, so it's actually, I think we actually have a bug. Maybe we found a bug in Wireshark. So you're going to send these requests to send, and when the request gets sent, for sure the access point can hear them, right? I mean, if the access point can't hear your request to send, it's like the teacher not seeing you raise your hand. So it's essentially like you're not participating in class. And you're not on the Wi-Fi network at all if the access point can't hear you. You couldn't connect to it anyway. So this is like seeing a bar of the Starbucks Google Wi-Fi hotspot, but you still can't connect to it because you're a little too far away. So you don't really successfully associate with the network. So that's how we do it. And then when the access point hears us, it sends a clear to send. You have permission to send back. Now, if I and another user try to send a request to send at the same time, it's possible that our data arrives at the same moment at the access point and is garbled. And so the access point, in fact, hears nothing. Well, nothing actionable. I mean, again, these are antennas, so it can receive data from any kind of technology. It could be a microwave oven, a portable, old-style portable phone, etc. So in this case, there's no action for the access point to take. And A and B don't know what's going on. They don't know why they didn't get permission to send. Maybe somebody else raised their hand. Maybe they never got their data sent. Maybe their antenna fell off. Maybe the receiver is rebooting or not there, or they walked too far away, or who knows why. But whatever the reason, it's unimportant. Their little algorithm, their finite state machine, has to do the same thing, which is resend again, try again. But just in case it was because of a collision with another request to send, they'll roll a random number and wait a random amount of time before they try their request again, to keep everybody from, like, 100 people ask for a request and they all collide. They all stop for a moment, they ask again, and just it's going to repeat infinitely. So to keep that from happening, we do what we did on Ethernet, which is if we think something's wrong, we'll try again, but we'll back off a little bit for a random amount of time. So that's what you see happening with A when it makes the second request. B has not yet had its timer go off, fortunately. And so A's entire request arrives successfully at the access point, and the access point gives it permission to send by delivering a clear to send message back out. So here are, I think we did see a bunch of clear to sends in here, right? Here we go. So this so irritates me that I'm going to try capturing again, because I just do not understand how it could not grab the request to send. It's actually something's really weird. I've got something set wrong, very wrong in Wireshark. So I will try it one more time. I do want to try to show you guys. So once you get the clear to send, here's the deal. Everyone can hear the teacher call on the student. Everyone can hear the access point give permission to A to broadcast. So even though B could never hear, or whatever the other guy, B could never hear A, B can hear the access point give permission to A to talk. And so B knows to be quiet. B will not try to continue to send something. He will hear nothing that A is sending. He's too far away from A. But he heard the access point give permission. So he'll stop and wait for the amount of time required for A to finish transmitting. Make sense? Okay, let me see if I can get any better here. I do not know what I have done with this thing. It's like I apparently did not eat my Wheaties this morning. How very bizarre. What if I turn this off? I'm not going to see anything here. Well, lots of acts and things going back. And there are times when requests are not sent. It depends on the hotspot. You can blow this off and just try blasting your data out and just see what happens, to see if you get lucky. It's a little faster, but it only works if the device goes along with it. And there's so few people on Wi-Fi in here right now that maybe that's why I'm not seeing requests in. I'd have to dig into the config and figure out what's going on. But this one's using RTPP. Okay, so that's kind of what's going on here. Let's go see a simulator that makes this thing real. And that's what we're going to spend the last 10 minutes doing here. So in your simulations, and you have the links for this stuff, and you've had them all semester on the website, on the class folder. The very last two on that one page, the one that looks like this. And remember, there's another page out there, and the other page looks like this. Right, it's all green. So you've got a couple of them out here. This one has it for Chapter 7, 802.11 CSMA-CA without and with hidden terminals. So fancy way of saying without hidden terminals that not only can you hear the access point, but you can hear each other. So if I am on this one, I will hear your request to send. And so I can know to be quiet. I do not have to wait for the access point to call on you. I can hear you ask. So let's walk through what this looks like. So simulator, they use colors to describe things. I'm going to start it off. The carrier is free. I click on station 1. Station 1 sends a request to send. A clear to send is sent back by the access point. You begin sending your data. When you're done, you get an acknowledgement. Station 2 can now do it. It listens for the network. It's available, so it immediately tries sending a request to send. It gets a clear to send. It sends its data. The acknowledgement comes back. So what's important about this one is that as soon as I send anything on the wire, because the other guys are close enough to hear me, they immediately sense that something's going on the network. They immediately can tell the network is busy, as shown by the red bar. They don't know what's going on, but they know it's busy. So there's no point in them trying to send something right now because it's occupied. It could be garbage, it could be noise, but whatever it is, it's not available for you. You've done your carrier sense and you've detected that the network is busy. All right, so as soon as this entire packet is sent, station 2 and 3, they're like, aha, okay, so I thought it looked like it was going to be a request to send, and in fact it is. 1 has just sent a request to send. And since I was able to hear it, my conservative assumption should be that so was the access point. It's possible that somebody else sent a request to send also that I did not hear. In other words, I'm close enough to 1 that I can hear him, but maybe I'm not close enough to station 4. So maybe there's still a collision, and the teacher, in fact, will not give permission to station 1, but I'm going to be conservative, and I'm going to assume station 1 will. So as soon as I hear this request to send come out, I will start what's called nav mode, which is a waiting period. I'm going to not do anything on the network to give station 1 a chance to receive his clear to send his data, and get his acknowledgement back. And only then will I try again. All right, so if I reset this a little bit, I'm going to start 1, sending a packet again. And I'm going to hit 2. And so now I've created a conflict. 2 is now waiting to send something. And as soon as the network is available, it goes green again. 2 will try. But because the network was busy when I asked 2 to send something, and because therefore 2 had to wait before he could send something, the prudent action to take is to roll a random number and wait. Because if I was waiting for the instant that 1 was done, a bunch of other Wi-Fi senders might have been doing the same thing. And if we all pile on as soon as the network is free again, we're all going to collide. So when I have the situation that I have something to send and the network was busy when I was asked to send it, then when the network is free again, I will roll a random number that you see in the gray box, not very long in this case, and I will try sending again. So I'm going to do it again. I'm going to say 1 and 2. And if I'm lucky, I will have, remember the size of this gray box, I have one that's a different size now, right? So I can do 1, 2, and 3. 1, 2, 3. Well, I did 1, 2, 2. Oh well. It doesn't. There's no guarantee which order they're going to happen. So in this case, 1, 2, and 3 all had something to send, or 2 and 3 did. 2 was rolled a random number, but before his random number expired, giving him permission to try, 3, who had also rolled a random number, since they both were asked to send something when the network was busy with 1, when it became free, they both rolled a random number, and 3 rolled a smaller one. Because 3's finished, and he sent a request to send. And at that point, 2 went, well, I've missed my chance. I waited too long, somebody else is now using the network. That's just the way it goes. So I'm going to have to wait until the network's free again, and then I'll roll another random number. So right now, 2 has 2 packets in queue. 3 has 1 packet in queue. I'm going to resume. I'm going to add a couple to 1s as well. And this time, poor 2, he still didn't get to send something. He rolled a very small random number, but 1 rolled a 0, basically, and immediately got to send. So he's still stuck with 2 things to send, and we do it again. Finally, 2 rolls a smaller one. He gets to send something. I'm going to click through. He's got something in queue now. This time, 1 wins. And we'll see what happens next time. This can happen, and it doesn't take very long for this to take place either. This is interesting. They both rolled the same random number. It's not an infinite series of random numbers. It's a set of them. And they both rolled the same one. And when they finished their random, the network still looked busy, so they transmitted. And you and I can see that they both transmitted at the same time. So you and I can see that this is going to be a collision. But again, we don't bother trying to detect collisions. There's no such technology in Wi-Fi, for example. All we can assume is we sent our request to send. Why didn't the access point respond? It got garbage. It didn't receive a clear request from anyone. It received whatever you call a combination of 2, but it wasn't a clear one. So it didn't have anything to send, and so he said nothing. They both are waiting and waiting and waiting, and they realize, oh my gosh, I'm not going to get called on. Let me try again, but it's probably because there was a collision. And the conservative thing to do would be to assume there was one, and therefore I'm going to wait before I send something else. I roll a random number. They rolled enormous random numbers. 3s was smaller, and he got to send something. And now he's done. There will be no other competition. But he doesn't know that. He still has to roll a random number and wait, and this time he's done. All right, so that's with no hidden terminals. As soon as somebody sends anything on the wire, like right here, everybody else goes busy. The other way of doing this is when there are hidden terminals. And I will show you what this one looks like. Here, I'm barely in range of the access point, and I'm definitely not in range of anyone else. So I cannot hear what this person sends. I cannot hear what this person sends. So I will reset and start this one off. Now, the first thing you'll notice here is when I send something, nobody goes busy, right? Nobody went busy here or here because they're too far away from me. The access point can hear me, but they cannot. So this is going to cause problems. It's going to cause more collisions. If I can't hear when somebody else is using the network, I can't be polite and sit down and wait. In fact, the only way I know that the network is being utilized by someone is when I hear the access point say something. I'm within the access point's range, of course. So when the access point is done, then I recognize that it's a clear to send, and like, oh gosh, I didn't even hear the request, but here's the clear to send. So I will go into, again, what is called nav mode. The network is considered busy, and I will politely wait. But during this time, it's dangerous. I can compete with someone else, and I can show you that. So I'm going to resume. I'm going to go 1, 2, 1, 2, 1, 2, 1. All right, well, right off the bat, we see it. I mean, I could do this 1,000 times, well, 10 times and not see it. Good God, this is like really bad. All right, so let's decipher what's going on here. 1 sends a request to send. In the middle of him sending his request to send, 2 starts to send a request to send. He didn't know 1 was talking. They both can sense that their network is busy because they're making it busy themselves. The access point hears neither. And 1 waits a random amount of time, and he starts to send again. 2 waits a random amount of time, and he starts to send again. Again, overlapping each other because they cannot hear each other this time. So again, 1 started to send a request to send. 2 just wrote right on top of it because they couldn't hear each other. The access point's like, I thought you were sending me a request to send, but then it went crazy. And then I got somebody else's, the end of their request to send. So that's like not valid. I'm not going to send anything. They wait, they try again, same thing happens again. They wait. This time, 1 gets it out the door successfully. 2 realizes the network is busy and stops. The network allows 1 to send his data. They both have bunches of stuff to send. They do the same stupid thing again by chance. Then this time 1 gets something else to send. And you see his back off. They're counting down the random back off times here. And this time 1 gets something to send again. They're going to roll random numbers here. Watch these counters. This one rolled a very short one. This one had a 4. I mean, this guy's like 25 now, right? He's just like in huge, huge trouble. He cannot hear 1 send. So look at what happens in this case. 1 sends a request to send. 2 cannot hear it. 2 starts to send a request to send. At the same time, the access point is giving the clear to send. Who is this clear to send for? It's for station 1, obviously because 1 started to send. So how does TuTh's transmission of a request not interfere with that? Yeah, station 1 cannot hear station 2. And remember the attenuation problem? While the access point is talking, it's the whole piece of gum. All he gets from station 2 is part of the bubble. The difference in signal strength is so intense that the access point never hears station 2. When you are singing at the opera at the top of your lungs on stage, you cannot hear someone whispering in the audience. If you were totally silent on stage, you probably could. Why is this little stretch while I'm doing this? You probably could hear them on stage, but because you're talking, you can't. So the access point is not bothered at all by station 2's transmission because it's too weak. He is blasting out at the top of his lungs, station 1 may transmit, and station 1 does. All right, so 1's confused, doesn't know what's going on. He rolls a random number. The whole time the network's really busy, but he doesn't know it. Station 3 knows it because station 3 was never talking. He heard the whole thing. He heard the access point give station 1 permission to send. So he went into network access point. He was busy blabbing when that happened, so he never heard it. So he's still green. So he's trying to send, getting ready to send another request. And he hears an acknowledgement come back from the access point. He's like, God, why am I the last one to know what's going on this network? So he waits, and because he doesn't know anybody else is in queue, he's counting down. He will try again. He will be successful. He will get 1 packet out. And then he has another one to send, but it was busy when he was originally asked, so he will wait a random time again. He will get this one out the door, and he has 2 more. This time he rolls a 6, and then he wraps up. All right? Make sense? So the simulators are fun. I will try to give you guys a fun problem that maybe we'll do on Wednesday together, but I'm going to give you one of these to try and label, and I want us to be able to do a basic one on the final. All right, it's a fun simulator. I encourage you to play with it. All right, that's all we have time for today, guys. Thank you very much for your attention. Hang in there, and I will see you on Thursday. Make sure I don't have one missing anything. Yeah, we have a huge crowd out there. Awesome. Bye, everybody.